G'day flatties and globe defenders, it's Critical Thing from Down Under, and I'm at the shopping mall and I'm thinking about measuring the radius of the Earth by presupposing it's flat. We get a lot of people say that you can only measure R by presupposing globe, but that's just not right. It can be done just by starting out with the assumption and the presupposition that the Earth is flat, and you can calculate R from that, and I'm going to show you how it's done.
Right. Well, to start with, I'll point out that every single quote-unquote proof of the globe will start with the presupposition that you're on a sphere. So the first thing you do with every globe example is place the subject on a sphere.
It's so easy to prove this buffet is wrong. We'll start with the presupposition that it's flat. Here's a picture of a ship. We will assume this picture is taken on a flat Earth. That is, we'll presuppose a flat Earth. Now we will measure the height of the top of the ship above sea level from this picture. Here's the metadata for that picture. So you can see the dimensions in pixels, the date and time it was taken, and you can see we're presupposing flat Earth there. I've put it in a folder called Flat Earth, and the GPS coordinates are not on this picture because the P1000 doesn't have a GPS in it, and I didn't have it linked to my smartphone at the time, but I know the GPS coordinates. I've taken the GPS coordinates of the ship anyway. Now this ship was at anchor, and the time there is about half an hour after I took that picture. The assumption is that the ship wouldn't have moved because it's at anchor. Now it may have moved a little bit because the ship can swing around the anchor, and that introduces a small amount of error into the calculation, but that's very close. And my observation point has been previously documented at Moffat Beach. It's 24 meters in height, and its coordinates are shown at the bottom there. Now when we put these coordinates into the geodata source distance calculator, we get the distance to the ship is 12.82 kilometers. Now then we can calculate the height of the ship from the observed reality. From the photo I get the zoom factor is 306 millimeters. The pixel height is also 3456 pixels from the metadata for the photo, and I've measured the pixel height of the ship at 584 pixels. The P1000 sensor height is 4.55 millimeters. Now we work out the field of view equation, and this you can get from doing Google search, but it's 2 times the arctan, and you take 0.5 times the sensor height over the zoom factor, and that will give you the field of view of the camera at that particular zoom factor or focal length. Now we plug the numbers into this equation, and we get that the field of view in that particular photo is 0.851935 degrees. That's probably more decimal points than we need because the accuracy is affected by the distance to the ship there, but that particular field of view is good, very good enough for making this calculation. So the angular height of the ship then is calculated out by taking the 584 pixels out of 3,456 pixels, and it's a simple ratio to work out that the angular height of the ship is 0.14396 degrees. And then using the triangle formula, I'll show you how that's done in a minute, we work out that the height of ship is 32.2 meters. Previously, I had estimated the size of the ship to be 33 meters. And so from the top of the ship to the water, this is how it's calculated. Now, I've assumed that the angle is close to 90 degrees, and it is very close. It's not exactly 90 degrees, but that gives such a minuscule difference to the calculation of the height that it doesn't really matter. The angle is very small, and the 32.2 is accurate to that 1 decimal place. So I then can calculate where the level line of sight crosses the ship. So there is assuming that the Earth is flat, there is some point on the ship that is 24 meters high, which matches the same height as the observer, making that a horizontal line on a flat Earth. Now 584 pixels measures 32.2 meters, therefore 24 meters measures 435 pixels from the bottom of the ship. And I've drawn that line here, which is the horizontal level line assuming flat Earth. But now then we have a problem. There is a horizon there, and the water should extend. On a flat Earth, the water would extend and it would rise to the eye level, which is 24 meters and represented by that red line. And I have constructed this picture, people call it Photoshop, for illustrating that this is what we might see on a flat Earth. The horizon would not cut off like that. The horizon would be in the distance, and it would be more hazy than that because it would be a very long way away, but that's not what we see. And some people argue that this horizon is here because we cannot see the sea beyond it, that this horizon represents some limit of sight or something. Now this will be the subject of another video at some time, but right now this is can be shown to be complete bollocks by this picture. This picture shows that the sun, which is even on a flat Earth at this point will be many thousands of miles away, and we know it to be 93 million miles away thereabouts, but somehow the light of the sun is blocked exactly where we see the horizon is. Now, isn't that an amazing coincidence? No, it's not a coincidence. I was just joking there. But here's a picture I've taken of that same sunset a little bit earlier, and you can make out a horizon there, and when the sun goes down and below the horizon, the light from the sun is blocked at that exact same point. So there you cannot argue that this is a limit of sight. It's not a limit of sight. I can see 93 million miles past it. So it's complete bunkum that might be a limit of sight. Now I'll get to what are we going to do? What are we going to do about this? We've assumed that the Earth is flat, and we do not observe what we would observe on a flat Earth. So we have to then change our assumption based on what we observe, observation of reality does not fit our assumption. So taking that assumption as, well, let's just say that the surface might be curved, which would cause the horizon to drop like that. Then we can calculate, well, what would be the radius of a sphere that caused that horizon drop? And I'll get onto that very, very shortly. But first, we will have to endure a little bit of maths because that's necessary to describe what it is that I'm doing here. This diagram here is my line of sight diagram. I've drawn this here assuming that the Earth is flat at this point. We've got our top of the ship here, which is 32.2 meters above the surface of the what should be level water on a flat Earth. Now this is drawn as looking straight out, but it's technically not. If this was flat, the 24-meter line, which is this red line, would be the eye level and horizontal line. But that's why it's not to scale, it's just a depiction, so don't pick on that. And so the angle I've calculated, the angular size of the ship, that has given me the 32.2 meters. Now, the drop to the horizon from the eye level is 24 meters. 24 meters is this red line on the ship. I've calculated from the photograph, I've taken how many pixels there is between where the horizon appears on that ship and the 24 meters. And counting those pixels, that gives me a degrees of horizon drop of 0.0968776 degrees. And remember, this is assuming that it's flat. But as I've explained, the assumption that it's flat is not holding up because of the horizon drop. And this has got nothing to do with any presupposition of globe or any historical measurements that anyone might have done. This is an observation that I did myself and easily measurable. The horizontal line is easily measurable on the ship. As I've made measurements, I've measured the distance to the ship, and now I'm applying logic that says that that is the horizon. And the logic is dictated by the fact that I can see the sun at that horizon. So the horizon is not anywhere else, and we must trust our senses. And my eyes are telling me that's where the horizon is. The sun's telling me that's where the horizon is. The ship's telling me that's where the horizon is. So this is not an assumption. This is not a fantasy. This is real. Now, to calculate R using a horizon drop, the horizon does drop away, so we're going to change now our hypothesis that it's not flat, that is in fact a sphere. So how would we calculate the radius of that sphere given a horizon drop? Now the maths is here and it's been done elsewhere, and I'm sorry if it looks a little bit complicated, but this is just pretty basic trigonometry and algebra. The angle to the horizon drop is A, and if you apply all the angles in there, you get the formula for the radius of the Earth is your height, which is your eye level height, which is 24 meters, times the cosine of the angle, divided by 1 minus cosine of the angle, and that will give you the radius. Now, then, what's happened here now, once we've got a radius of an Earth, we go back to our original assumption. Our original assumption was that it's flat. Now, this no longer holds because of the horizon drop. And now we have calculated, I can tell you that this calculates out for that horizon drop around 16,000 kilometers radius. Now you say we know that the radius of the Earth is 6,371. But remember, this is assuming that the Earth is flat. So now we've got to make some adjustments now because it's not flat. So we've got to make this adjustment, like there's a slight curve there, which is the blue line. It's no longer flat. The eye level is now not 24 meters up this ship, which is this grey line. It's no longer 24 meters above the ocean on that ship, because the water drops away with this curve, which is demonstrated because the horizon drops away. So we have to work out what this extra drop is to adjust for the fact that our angle from eye level to the horizon is now going to increase by a little bit because we now have a sphere of 16,000 odd kilometers. So we have to calculate this extra little piece of drop. And I do this here. Now I use an approximation here. The reason why I use this approximation, because this distance is 12 kilometers and it is very, very small compared to the circumference of the Earth. Hence, we can approximate the length of this arc with this distance to the ship. Now, over 12 kilometers, the distance difference is about 8 millimeters. So we're not losing anything in accuracy by making this simplification, because the accuracy of the distance to the ship and the height above sea level, I don't know the exact error rate there, but I'm thinking it's somewhere in the order of 5%. It is possible that we're like out by a meter on the height. It is possible we're out by maybe, could be 30 meters on the distance. So 8 millimeters is nothing. So using this simplification and a little bit of trigonometry, we can calculate how much the ship has dropped down at 12 kilometers. So we have to then add that drop to the angle from eye level for the horizon drop. And I do the trig there, and x, which is our extra drop, is calculated, is the radius that we already have, which in this case will be 16,000, and then multiplied by 1 minus the cosine and the arc sine of d over r. So it all looks a little bit complicated, but this is how you work things out without just looking out and say it looks flat to me, because it will look flat. These numbers are very small in terms of angles and drops, so your eye cannot exactly distinguish a horizon drop until you take a picture, what I have of that ship. Then you can tell that there's a horizon, definitely horizon drop. There's no mistaking it. They don't even have to point a tube at it for that one, because the ship's out there as our marker. And the horizontal line is very easy to determine. And because it's curved, the horizontal line is going to be now a little bit bigger by x. And I actually have then programmed all this into a Python program. So this is an iterative process. So we've come up with a 16,000 odd kilometers radius. Now we have to adjust our drop for that. because our original calculation for the angle of the horizon drop is now wrong. So we now calculate the drop and then calculate a new R. And then according to the new R, there'll be a little bit more drop, if the R will be less, and this will slowly converge into a number that is agreeing with the drop on the sphere that we're observing on. So in order that how that works, and I've got the output here. So as you can see, the first R we got was 16,000 and the horizon drop angle 0.0969. And the second iteration through, we got 11,000, and you can see it does converge. It converges until finally we only get, I've just stopped it at the nearest kilometre, 7,213 kilometres. Now, this is just all done. Remember, it's starting out with the assumption that it's flat. But starting out with that assumption, we've got an answer 7,213 kilometres. Now, this is a little bit bigger than what I was expecting. 6,213, sorry, not 6,371 is the accepted figure. So, and I did not expect the error to be so large. So I'm thinking about this, well, we all talk about 7 over 6R and how refraction is present nearly, nearly all the time there's some refraction. So if we do say that refraction is a thing and we take 7213 and we apply 7 over 6 factor to that, we end up with an answer 6,182. So if there was refraction on that day, then the refraction combined with our error in measurement will give that figure of 7,213. So the fact that it looks like a bigger radius because of refraction is does comport with what we know about 7 over 6R. So we've demonstrated here it's not flat, it's a sphere. There appears to be refraction at work because of what we've measured, and our numbers come up looking pretty good. And I've done this all without consulting NASA, without assuming that anyone else has done anything to measure R, other than the fact that I know it's been measured in 6,371 and I've compared my answer to that. And that's it. There's no trickery, nothing. It's just straight observation of reality and then applying principles of geometry and trigonometry to that. So there you have it. It's not flat. We can assume flat and calculate R.
Right. Well, to start with, I'll point out that every single quote unquote proof of the globe will start with the presupposition that you're on a sphere.